So today we're starting section 3.7, which is on polynomial and rational inequalities. So first we need to define what a polynomial inequality is. So from the intermediate value theorem, we discussed earlier, we know that polynomials do not change signs between neighboring zeros. So graphically, this means that between successive x-intercepts, the graph of our polynomial p is entirely above or below the x-axis. So what this will look like is we have a graph. Extend this a little bit. Okay, so here, let's call this point -3, this point -1, this point 2, and this point 4. Then we can shade under our graphs in between our successive zeros. And we can see that in between each one, we have either negative regions or positive regions. All right, and so when we write this, we will write that p of x is less than or equal to 0 for x in -3 to -1 union 2 to 4. And then p of x is greater than or equal to 0 for x in, when we work with infinity, we do a regular parenthesis instead of a hard bracket. So the -infinity to -3 union -1 to 2, and then union 4 to positive infinity. And so here we have these different regions, and you'll notice that we have a hard bracket because in each one of them we have a less than or equal to 0. If we had just a strict inequality, which doesn't have the equal to, then if we just had p of x less than 0, then it would be the same intervals, except for they are soft brackets because we do not include the points where they equal 0. And similarly for the greater than 0 case. So that's the difference when we're looking at graphs between the less than or equal to and the just strict less than or greater than, because with our zeros here at exactly x equals -3, -1, 2, and 4. Okay, so now we can move on to solving polynomial inequalities. So here we're going to define a couple of steps that'll help us learn how to solve these. So first, we're going to move all terms to one side. This will let us get a 0 on one side, and that way when we look at a graph, it'll help us determine if it's less than or greater than 0, because we can look at a graph and it's either above or below the x-axis, and it just makes it a little easier to find these regions. And then 2, we're going to factor the polynomial. And this will let us find the real zeros. And remember, our real zeros are also our x-intercepts. All right, and then 3, we're going to find the intervals. So these intervals are determined by the real zeros. And then 4th, we're going to make a table or diagram. And we're going to use test values to determine the sign in each interval. And then finally, step 5, we're going to solve. So here we're going to determine our solution and check endpoints. All right, and to illustrate this, we're going to do an example. All right, so we're going to solve 2x cubed plus x squared plus 6 greater than or equal to 13x. So we're going to move this 13x over to get everything on one side. So we're going to have 2x cubed plus x squared minus 13x plus 6 is greater than or equal to 0. So here we subtracted our 13x from both sides of our inequality. Then second, we're going to factor. And I have found the zeros beforehand, just so you don't have to see me run through factoring. If you're still confused on how to quickly factor, go back and reference the lecture on factoring. Right, so it'll become factored into x minus 2, 2x minus 1, and x plus 3. And this is greater than or equal to 0. So this means that our zeros are 2, 1/2, and -3. All right, so now we are going to determine our intervals. So we're going to have -∞ to, to -3, -3 to 1/2, 1/2 to 2, and 2 to positive infinity. And so I just listed our zeros in order of smallest to greatest and just kind of went through and created our intervals in that order. And we divide them where we have a 0. All right. And so now 4, we're going to make our table. So I normally draw a number line to kind of determine what our zeros will be. So I know that we have a 0 at -3, at 1/2, and at 2. So this kind of creates a table with 4 parts. So if we're looking at values less than -3, I'll plug in something like -4. And so if we were to check this, I will run through and just kind of examine what happens if we plug in -4. And I usually will look at the factored form up here to help with that calculation. So -4 minus 2, that's negative. -4 times 2 is -8 minus 1, that's negative. And then -4 plus 3, that's -1, so that's also negative. So that lets me know that this whole region is negative. And then in between -3 and 1/2, I like to pick 0 when I can because that'll make it easy. And then I'll see that that'll be 6. So that means that that is positive. Because that one you can just plug 0 into your original equation of 2x cubed plus x squared minus 13x plus 6, because you know the only thing that'll come out is a 6. And then in between 1/2 and 2, I'll use 1. So 1 minus 2, that's -1. 2 times 1, that's 2, minus 1 is 1, so that's a positive number. And then x plus 3, that's positive, or 1 plus 3, that's 4, which is positive. So then we have 1 negative times 2 positives. That'll make it the whole region negative. All right, and then now we need to pick a number bigger than 2. So we can pick 3. So 3 minus 2 is 1, so that's positive. 3 times 2 is 6, minus 1 is 5, that's positive. And then 2 plus 3, that's 5, and that's positive. So here, this region is positive. Okay, so now, and remember, we're trying to find which regions are greater than 0, so that are these positive regions here. These are the regions we want to work with. So now we're going to test our endpoints of our intervals, which are the intervals we want to work with, are -3 to 1/2 and 2 to infinity. So we can't check infinity. That one will stay with the soft bracket. But if we plug in -3, 1/2, and 2, we'll see up here with our factored form, we will get a 0 with any of those. And since we have a greater than or equal to 0, that means that they're included. So this means in our step 5, when we are solving, that means for x in hard bracket, -3 to 1/2, hard bracket, union 2 to infinity, x's in either of these intervals satisfy the inequality. All right, and so that's how we finish our first example. And now moving forward, we're going to do another example. So we're going to solve for 3x to the 4th minus x squared minus 4 less than 2x cubed plus 12x. So first, we're going to move everything to one side. So I'm going to have a 3x to the fourth minus 2x cubed minus x squared minus 12x minus 4 is less than 0. So for 2, I'm actually going to show the steps on how to factor this one for a bit of review. So let's put factoring. So the possible zeros, and this is from our rational zeros theorem. So they are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 1/3, plus or minus 2/3, and plus or minus 4/3. And this is because up here, our leading coefficient has a 3, and the factors of 3 are plus or minus 1 and plus or minus 3. And our factors of 4 are plus or minus 1, 2, or 4. So this one, these areas here, are when we're looking at factors plus or minus 1 of 3. And here is when we're looking at factors plus or minus 3 of 3. Because you'll recall from the rational zeros theorem that our solution will be a fraction with the factors of our end coefficient or our constant term, -4, divided by the factors of our leading coefficient. Okay, so now we're going to check which ones are actually zeros. And we will find that 2 and -1/3 are zeros. So factoring them out with synthetic division, I'm going to work with 2 first. We'll see that 2 dividing 3, -2, -1, -12, -4, bring our 3 down. We multiply and we get a 6. We add and we get a 4. We multiply, get an 8. Add, get a 7. Multiply, get a 14. Add, get a 2. Multiply, get a 4. Add, get a 0. This checks because this makes sure that we know it's a 0. So then we will get the equation 3x cubed plus 4x squared plus 7x plus 2. And now since we know that both 2 and -3 are zeros, both of those terms will divide out of our equation. So that means we can still divide this next one by -1/3. Using synthetic again, we will use 3, 4, 7, 2. We'll bring the 3 down. All right, so multiplying, we get a -1. Adding, we'll get a 3. Multiplying again, a -1. Adding, we will get a 6. And multiplying, we will get a -2. Adding, we will get a 0. This also checks out. And so here we will get a 3x squared plus 3x plus 6, which equals 3x squared plus x plus 2. But here we will have complex roots. So for this polynomial inequality, we do not need to go further because we only care about the real roots in this situation. Okay, so factored, we have x minus 2, x plus 1/3, and x squared plus x plus 2. With real zeros, 2 and -1/3. All right, so now going back to our original problem of solving the inequality, we'll move on to step 3, which is creating our intervals. So that will be -∞ to -1/3, -1/3 to 2, and 2 to positive infinity. All right. And now we are going to create our diagram. With our number line here with -1/3 and 2. If we check a number smaller than -1/3, like -1, we will see that we will end up with a positive output. And y'all can check this similarly to how we did the first example, just kind of plugging in the value into your polynomial and seeing if the output is positive or negative. And then we will check in between, and we will see that, for example, if we use 0 in the original equation, we will end up with a -4, which is negative. And then if we pick a number bigger than 2 and plug it in, we will see that we get a positive value. And then if we check our endpoints of -1/3 and 2, we will see that these do not satisfy because we only have a strict inequality. We do not include 0 in this one. So that means x in -1/3 to 2 with soft brackets satisfy the inequality. And I'm going to rewrite the inequality now since it was at the beginning of this example. Satisfy the inequality 3x to the 4th minus x squared minus 4 less than 2x cubed plus 12x. So for values in this interval, that will make this expression true. Okay, so now we're going to move on to rational inequalities. All right, so first we need to recall that rational functions are not always continuous. We will have asymptotes or parts where we just have a little hole there, like discussed in the last section. So first we're going to start with a definition. And it's going to be a cut point. So if r of x equaling p of x over q of x is a rational function, the cut points of r are the values of x at which either p of x equals 0 or q of x equals 0. In other words, I don't know why I have a capital Q there. Sorry, that should be lowercase. So in other words, the cut points are the zeros of the numerator and denominators. All right, so now I'm going to talk through the procedure of solving rational inequalities. There we go. Okay, so, oops, dropped my pen. 1. So first, we're going to move all terms to one side. and bring all quotients to a common denominator. Two, we're going to factor the numerator and the denominator. And this will let us find our cut points. All right, 3, we're going to find the intervals. And this time it is in between cut points. Right. 4, we're going to make a table or diagram. To determine the sign of our function. And then 5, we're going to solve. We have to remember to check endpoints. All right, so to do this, we're going to look at an example. So if we look at when 1 minus 2x over x squared minus 2x minus 3 is greater than or equal to 1. So first, we're going to bring everything over to one side. So we'll have a 1 minus 2x over x squared minus 2x minus 3 minus 1. And now we're going to have this 1, we're going to multiply by x squared minus 2x minus 3 over x squared minus 2x minus 3 to give it a common denominator. So then we'll have 1 minus 2x minus x squared plus 2x plus 3 all over x squared minus 2x minus 3. And then simplifying, we will end up with 4 minus x squared over x squared minus 2x minus 3 greater than or equal to 0, greater than or equal to 0. All right, so now moving on to step 2, we're going to factor and find our cut points. So the numerator, we will get 2 minus x and 2 plus x. Then in the denominator, we will get x minus 3 and x plus 1. And you might have noticed that in the numerator, I wrote the constant before the x. This was only because we will have a 2 minus x, and I just think it looks a little neater to write it than negative x plus 2. But both ways are correct. So if you would rather have the x in front, that is the exact same way to write it. All right, and so here our cut points are -2, -1, 2, and 3. Because these are where we will have zeros in either the numerator or the denominator. So that means that our intervals are -infinity to -2, -2 to -1, -1 to 2, 2 to 3, and 3 to infinity. All right, moving on to our diagram. It's going to be a similar thing where we have our number line, say -2, -1, 2, and 3. So here, if we take a number smaller than -2, like -3, we will see that we will get a positive value, then a negative, and a negative. So overall, this means that since we have an odd number of negatives, the whole thing is negative. Then in between -2 and -1, we can do something like -1.5, and we will see that we get positive, positive over negative and a negative. So that means since we have two negatives, those will cancel and make a positive. Then in between -1 and 2, we can just use a 0. And we will get a positive, positive over negative, positive. So this means since we have only one negative, that makes the whole thing negative. And in between 2 and 3, here you could pick something like 2.5, and we will get a negative, a positive over a negative, and a positive. Two negatives, this will cancel and make a positive. And then if we pick something larger than 3, we'll have a negative, a positive over a positive, and a positive. So there we have a negative. Okay. And also something that we can observe here is that 2 and -2, these are zeros. These go to 0. Whereas -1 and 3, these will be our vertical asymptotes. So these will go to positive or negative infinity. This is something just to remember about rational functions. But we know when we have something that is greater than or equal to 0. So 5, we can write our intervals. And so what's important about these zeros and these asymptotes are when we plug in -2, because this is when we're checking our cut points, -2 goes to 0, so that means we get to include it in our interval. So it's -2, 2. But since we never reach -1 because there's an asymptote there, we have a soft bracket. And similarly, with +2, we have a 0, so we know that we can reach it, versus with 3, we have an asymptote, so we will not reach it. So that, again, we have a soft bracket. All right. So I'm going to quickly run through another example just to help illustrate this one more time. So we're going to look at when x squared minus 4x plus 3 over x squared minus 4x minus 5 is greater than or equal to 0. 1, we're done. It's already all on one side. All right, so for 2, when we factor, we will see that we have an x minus 3, an x minus 1 over x minus 5 times x plus 1 with our cut points. -1, 1, 3, and 5. So in 3, our intervals are -infinity to -1, -1 to 1, 1 to 3, 3 to 5, and 5 to positive infinity. And then 4, we're going to make our table. So we will have -1, 1, 3, and 5. So just quickly running through, we will get a negative, negative over a negative and a negative. So this becomes positive. -1 is a vertical asymptote. So just recalling that, that'll go to infinity. And then in between -1 and 1, let's pick 0. And we'll see that we get a negative number because we'll have a negative over a negative and a positive. Oh, that 1 shouldn't be there. Oops. There we go. So this is negative. In between 1 and 3, we will get a negative, positive over a negative and a positive. So this is positive. 1, this is a 0, and 3, this is a 0. And then in between 3 and 5, we will get a positive, a negative, a positive. So overall a negative. And our 5 is also a vertical asymptote, so this will also go towards infinity. And anything bigger than 5, we will see we have a positive, 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 positive. So overall, all positive. And the positives are what we want for our inequality. And then when we check our endpoints again, recall this is a greater than or equal to, so we get to include our 0. So that means we have negative infinity to -1, not counting -1 because it's an asymptote, union 1 to 3, because 1 and 3 are both zeros, so we reach there, union, oh, +5, not -5, whoops, 5 to positive infinity. And again, not including 5 because 5 is where we will have a vertical asymptote. So there we go. This is ending chapter 3. Your next lecture will be a midterm review video, but then moving on next week, we will be looking at chapter 4. All right. Thank you guys so much.